Jnanam Paramam Dheyam. Knowledge is supreme.
Now, I want to begin a new study of field extensions, which are so-called normal extensions. In general, we have seen already normality means splitting of a polynomial. So, we have to relate this normality property with the set of zeros of polynomials. So, I want to study more generally the connection between the zeros and so-called embeddings. So, what does this mean? So, let me first explain what is an embedding. So, suppose I have a field extension L over K, field extension. So, that means we have L is a field and it contains K. This is an extension of K. That means there is an inclusion map. Now, suppose I have another extension E. This is another field extension of, this is also field extension. And if there is a field homomorphism here, field homomorphism means it should respect addition, it should respect multiplication, and 1 should go to 1. That is a field homomorphism. Because this L is a field, this will always be injective. This is always injective. So, I will call it this sigma, I will call it K embedding if it commutes with this, it is K linear. If K is a subfield of E, K is also subfield of L, and if the sigma is field homomorphism plus K linear. So, remember all these together we have been saying the sigma is a K algebra homomorphism. So, such a sigma is called K embedding. Of L in E. So, for example, we have been studying when E equal to L, when E equal to L, this is precisely what we were considering the Galois group of L. So, now precisely we will put down the definition and then we will indicate its connection with the zeros of polynomials. Alright, so in some sense this is more general than the Galois group. So, our notation, so definition K field and L over K and E over K are two field extensions. Then M for embeddings, K as K embeddings. So, I will not write KLG here, that is okay, let us write K L to E. These are precisely, this is a set of all sigma. Sigma is from L to E such that sigma is a K algebra homomorphism. So, we want to study this set, and as usual we will study it for finite L over K and decide how many elements this set has, exactly like what we studied Galois groups. Alright, so I will, very simple cases I will do it first. So this is what we want to study. We want to study this set. So let us do it a little bit more general. So suppose I have a field K is a field, and I have a polynomial f in Kx, and I have A be a K algebra. Remember, A need not be a field. A is just a K algebra. A could be polynomial algebra, or A could be just K power n, or quotient of the polynomial algebra, and so on. So A is any K algebra. Then I want to write a proposition first. Proposition. There is a natural bijective map from where between K algebra homomorphisms and zeros. So what is the map? So on one side we have home K algebras from Kx mod ideal generated by F and A. No, before I go on, this is also K algebra. This Kx is a K algebra, polynomial algebra, and modulo that this is also K algebra. This is a simple K algebra. It may not be a field because F may not be irreducible. I have taken arbitrary F. So this may not be a field. Therefore, I don't write M. I write homomorphism from as a K algebra from this residue algebra to A. This is the set of homomorphisms. This is what I am referring to. And to zeros. Which zeros? V, A, F. And what is this by definition? This by definition, all those elements A in A such that F of A is 0. These are the zeros of F in A. That's why this notation is just, and there is a natural map here which is bijective. That is the assertion. Bijective, and I have to explain you the word natural. This is what we want to prove. This is a first easy observation, and as you will see, this observation is the same trick what I kept saying. This is the one trick which we will keep using in Galois theory again and again. That means homomorphism and zeros. So now I will explain what the natural means. Okay, the naturality means of the above map means the following. Whenever I have, for every K algebra homomorphism, phi from A to B. Now I have two, I will draw a diagram. So what we were considering was home K algebra Kx mod F to A and VAF, and this was the map we wanted to define. And on the other hand, this algebra homomorphism, this given algebra homomorphism will give us a map in this direction. Home K algebra from the same kx mod f comma b. What is the map? If I have homomorphism here, any sigma, where does this map goes? This has to use this phi. That means I will take this sigma and compose. This sigma is from this to this, and from A to B I can go. So this I will map it to phi compose sigma. This makes sense, which is an element here. So this is also, it will give me a map from VB to F. This also I will define, and this is the map we are defining. So this diagram is commutative. Now what should be this? This should be any element A here. I should check that phi of A should belong here. This is what we need to check. So that this diagram is commutative. Right? So therefore this map, in some sense it is very natural in this A. These are values in A, these are the zeros in A, these are the zeros in B. So naturality means for every K algebra homomorphism phi, the following diagram is commutative. It's a diagram of sets and maps, and one says it is commutative when there is only one point here where you can go from here, that is one way, other way is this. So this diagram should be commutative. So usually it is denoted like that. This symbol is used. That means whether you go this way or that way, it is same. Now this is so easy. You will see we have spent more time in the statement, so proof is so clear. Okay, so proof. So we want to give a map from home K algebra Kx mod f to that A. To A, given this, I want to get 0 out of this. So this I want to give a map this to VAF. I want to define a map here. So what do I have to do? That means suppose I have given sigma. Sigma is K algebra homomorphism from Kx mod f to A. This is given to us, and I want to associate a 0 of that. Okay, when this is given to us, that means we have given from Kx, there is a natural map here, this is a natural surjective map. That means I have given this, and what is this map is sigma is given to us, and I want to get a 0 of that. So that means what? So first of all, note that this map is uniquely determined if I know value on x. Therefore this map will be uniquely determined when I know its value on, if I denote the residue of capital X mod this f is small x, then it's enough. The sigma is uniquely determined by sigma of x. The sigma of x is an element in A. And this when should be this well defined? Only when f should go to 0 there in A. But where do f go? That we will write down very precisely. Where do f go? Once I know where x go, it is clear where f will go. So note that f of, if I apply sigma to f, what do I get? This is the trick I am saying. This is sigma is the K algebra homomorphism and f is a polynomial. So That means this will be f of sigma of x, and this is 0, we know, because the map is f should map to 0. So, therefore, this is given to us. That means what? That means the sigma x, this means sigma x indeed belong to the 0 of f in A, because this is an element in A. Therefore, we have a natural map, this sigma, which maps to sigma of x. This makes sense. And that is the map. This is so natural. And I want to check that this is bijective. Alright, but that bijectivity is clear because it is uniquely determined by x, the value of x. See, it is we have defined a map from here to here. This map is sigma going to sigma of x, and this sigma is uniquely determined by this. Therefore, this map is clearly injective, and it's clearly surjective also. So, this map is bijective, because if A were a 0, so injectivity is obviously clear because sigma is uniquely determined by this. That means the map is injective. So, to prove surjectivity, if A is an element in a 0 element in this, I could define a map from kx first to A. This map is, I have to give only for x, where does x go? X goes to A, and because this A is a 0 of f, so that is f of A is 0. Then this map, this K algebra homomorphism, obviously it will factor through kx mod f to this. This is my sigma then, and this small x here will go to that given A. Sigma is going to A, and A is sigma of x. I am not saying this map is injective, but whenever somebody is in the kernel, you can go mod it and you have a well defined map from here to here, and that gives you surjectivity of this map. So, this map is bijective. So, therefore, altogether we have proved our statement. So, it is one which relates the zeros with K algebra homomorphisms. Now, okay. So, some corollaries I want to write down from here. So, corollary, okay, let kx, k small x, be a simple field extension of K, and I am simple, be a simple algebraic, I wanted to say, algebraic field extension of K, then and E over K be any field extension. Then there is a natural bijection from where to where, that is home K algebra Kx, because it is algebraic, whether I write square bracket or round bracket it is same, and the values are in E to 0 set of the minimal polynomial of x over k in E. This map, there is a bijection, and what is the bijection? Take any sigma and map it to sigma of x. This was the trick we were using it earlier also. It is a natural bijection, and I have applied to the special case where A equal to the field actually E. And now in this case this is also field because I am taking a simple field extension. So therefore, instead of writing this, I will write M K algebra Kx E. So the simple field extension embedded in this how many other ways? So that is the sigma. So that to the zero set of this. And now in particular I will write down this obviously follows from the above very clearly. In particular, if you have a bijection, cardinalities are same. So cardinality of the number of embeddings, K algebra embeddings from the simple extension Kx to E, this number is same as the number of zeros of the minimal polynomial of x over k in E, but these zeros is definitely less equal to the degree of the minimal polynomial, and this minimal polynomial degree is precisely the degree of the field extension Kx over k. So you see the answer is very nice. So this bound you see here, this bound is not depending on this E. There is no E on this side, that is in between. So the number of embeddings from one field to the other field, we would like to say that it is bounded by somebody. Like we said, in case of a finite extension, the cardinality of the Galois group is bounded by the degree of the field extension. So therefore, I would like to prove, more generally I would prove, so this was part of the corollary. More generally, we will prove the following statement, not now but later, maybe couple of lectures above. So number of embeddings, K embeddings of L to E, where L over K is finite extension, if L over K finite field extension, and E over K any extension, any field extension. Then I want to prove this number of embeddings is bounded by the dimension of L over K. This is what I want to prove later. And what we have proved it today is for the simple extension. For simple extension, we know this. Okay. The theorem I want to state, which will support this claim, prepare this inequality. So theorem I want to state is the following. That is, this is extensions of embeddings. So the situation is the following. Let L over K be a finite field extension finite is I am assuming, and later on we can also drop finite and replace it by algebraic, but that I don't want to do it now, because essentially this course we are dealing with finite field extensions, but then when you want to drop this, you will have to do better cardinal arithmetic. All right, and M be a intermediary field extension. That is, M is a field in between. Okay, and we have given an element sigma belonging to the embedding, K algebra embedding of M to E. And I would like to extend it to L to E. And how many ways? So that is what I want to analyze the problem. So given this, so given sigma this, there exists, or let me write it, for every embedding sigma there exists a finite field extension E prime over E such that, okay, and finite field extension E prime over E and sigma prime belonging to embedding K algebra embedding of L to E prime such that if I restrict this sigma prime to M, I get back that sigma. This statement is very easy. We will prove it immediately. All right. So we want to. Before I go on to the proof, remember the title, extensions of embeddings. So this sigma is given to me embedding, and I want to extend it to a bigger field L. That is why extensions of embedding. This is very easy. Okay. So proof. So reduction to the, I will reduce the proof to the simple extension. Reduce the proof to the case of simple extensions. As follows. All right. So what to do? We have given L over K. L over K is given. Let me draw a diagram. So L over K is given to us, and M is here in between. And there is a map from M to E. And this is K linear. This is given to us sigma. This is contained here. This is contained here. And this diagram is commutative. That is precisely the meaning that sigma is K linear. All right. And this is our extension here, and we are looking for E prime, so that this is contained here. So I will draw that dotted. We are looking for this, and we are looking for this extension, sigma prime. This is what the problem is. We want to find E prime, which is also should be finite extension, such that this we should be able to extend it here. All right. So we know that L is finite. This is finite given to us. So we can do like this. So K is here, L is here, and L is generated by finitely many elements over K, x1 to xn. And there is a chain here. This is contained in Kx1, etc., etc. This is, so if you call this as K0, this is K1, this is Kn, and in between there will be generated, suppose it is generated by x1 to xr, this is Kr. This is what we have given, and I want to slowly, so without loss, first of all I can assume M equal to K, because I will replace M by K. If so, first of all we may assume M equal to K, because this part is not doing anything there. All these are extensions. So in M equal to K case, I have the chain, and I am going to find here, for this step I have to find E is given to us. E is an extension of this K. I will find E1, which is a finite extension, and then lift this map here, and keep doing it. So therefore, with this we only have to prove the following. We have to prove that, so we need to prove the following. So L is my simple extension over K, and I had another extension. This is field extension, and I had that, not the inclusion map, but I had the embedding. This is my sigma, and here I want to find E prime such that this is finite extension, and I want to extend this sigma to this sigma prime. That is the problem. All right. So what do we do? So this extension is uniquely determined by that mu xk. This is the minimal polynomial of x over k, which is a polynomial with coefficients in k, and let. So therefore, this polynomial also has, without loss I can assume this is injective. So therefore, look at the image of mu under this map. So mu xk, this is a polynomial in kx, and apply sigma to this. This is a polynomial in ex. This is simply, what you do is you take the coefficient of the minimal polynomial and apply sigma to them. So this is a polynomial here, and therefore I can enlarge this field E to field E prime such that, so let and enlarge E to the field E prime such that E prime contains a 0 y of the sigma mu xk. This such a field exists, and in fact we can choose a finite field extension. I don't even need all the zeros. I only want one zero to be contained in E prime. Such a thing is possible by Kroneker's theorem. Once I have that, then we are done, because how do I extend? How do I give a homomorphism from E to E prime? To give such a sigma prime K-algebra homomorphism, in the beginning lemma only we saw that this is equivalent to giving a 0 v prime of the minimal polynomial of x. But that is what we have chosen y here. So this y will correspond to sigma prime, and the sigma prime will map x to y. So the sigma prime maps x to y. So therefore there exists sigma prime, and therefore our problem is solved. Therefore that shows that given any embedding, I can always extend to the bigger fields, and I want to use this again and again. So this is also related to what is called the extensions are normal extensions. So this is what I will study in the next time I will study precisely what are normal field extensions and use this prerequisite to that normal extension. So with this I will stop, and we'll continue next time. Thank you.